Example 7.2, describe physically the behavior of the capacitor's voltage. Does it charge up or discharge? Calculate and plot the current Ix for t greater than 0. So we want to physically interpret. So let's physically interpret the capacitor's behavior or before the switch is thrown and then long after the switch is thrown. Okay, so let's look at this. So at t equal to 0 minus, the first thing that you should note here is that, look at this guy right here. Note that I can combine these into one resistor. So if you look at this, this is going to be 12 parallel to 2 plus 4, and that's going to give me a single resistor of 4K. So I don't really need the values, but that's just one resistor. So if I start to draw in what this circuit looks like at t equal to 0, we're seeing this. I have resistor that goes like this. I have that reduced resistor. Then I have another one. And then I know that it reaches steady state, so that's where the capacitor goes. And then I see that I have a resistor and a source right here. So when I'm looking at this, the only thing I have to add is I have to add the current source. So now look what's actually happening here. This source here is the current of the 4 amp source here. And then there's going to be a second current that's coming from this guy here. This is going to be the current of the 4-volt source. So what you're seeing here is that there are 2 sources feeding the voltage. Right? There's 2 sources feeding the voltage. Now look what happens. When the switch is thrown, it shorts out the 2 and the 4-volt source here. So at t equal to 0 plus, and then we're going to let that go to t equal to infinity, what we're seeing here is that because it gets shorted out, I'm now going to have this type of situation. So you're going to see that I'm going to have the resistor. I'm going to have this resistor. Let me bring this up a little bit higher. And then here's my open again. But now there's no source for the voltage source. And then the only thing that's feeding this capacitor now is this 4 amps. So what this means here is that there is only one source feeding the capacitor. So if I now look at this thing, this is going to be VC of 0 minus. When it reaches steady state, that's got to be VOC. So we expect here is that the capacitor discharges. So if it discharges, that means that VC of 0 minus has to be greater than VOC, which is the same as VC at infinity. So mathematically, that better be the case. Okay, so here we go. So now what we want to do here is that we want to calculate and plot Ix of t. And when you look at that Ix of t, note that that's going to be through that 2K resistor right there. So what I got to do here is that I got to remove that capacitor. Okay, I got to remove that capacitor. So I want to calculate this guy here, which is the same as one of the 2 ohm resistors as a function of time. So now that's my goal right here. So because this is a constant source, I'm going to use the physical Thevenin approach with this method 1. So here I go. I'm going to remove the capacitor and calculate VOC. So my first step is that I want to determine VC of 0 minus. Okay, that's my first step. So let's draw the circuit here. So the circuit is exactly the circuit that has the 4-volt source here. So it's really this circuit that I got to write at t equal to 0. So here I go. So if I draw this out, I'm going to look something like this here. So I'm going to have I have a 2 ohm there, another 2 ohm here, and this is my combined resistor due to resistor reduction. I have this node, I have that node, then I have a 2, then I have my voltage source, and then I have finally my current source right here. And then this guy's going to come right here. So now let's start putting in my values. So this is a 4, this is a 2, this is a 2, this is a 2, this is 4 volt, and then this is my 4 amp source right there. So I think what I'm going to do here is the question is, I've now opened the capacitor, and so now I got to calculate VOC. So note, they did not tell me what is positive and what is negative. So I'm going to figure out what is positive and negative on that capacitor by just analyzing this thing. So the first thing I'm going to do is that I think I'm going to pick a ground, and I think a good ground for me is to pick it right here. So here is my ground right there. So this automatically tells me that this node right here, of course, is 4 volts. So now what I'm going to look at here is that look at that 4 amp source here. So if I look at that thing, we could then say that because of the open, this becomes a series circuit. I could use node, I could use mesh if I wanted to, but what I'm going to do here is that follow the 4 amp source. Okay, so let's look at that source. So what I'm seeing here is that this current comes here, right? There's 4 amps. So note that that means here is that that current is also coming in this direction. And then it's going to move in this direction as well. Now look what happens here. Because of that open, you could see that if I go to the right branch for the two ohm resistors, note that it's got to split it because the right side is 4, the left is 4. So that means I'm splitting this where 2 amps goes this way and 2 amps go that way. So look what happens now. The first thing that I'm going to do is that if I follow the current, note that this guy is plus and minus here. And for the lack of better language, I'm going to call this resistor X. So now look what happens. So if I look at the voltage of Vx, note that that's the voltage of that 2 ohm right there. So I know the polarity because of the direction of the current, but this immediately tells me that this node right here should be 2 times 4 according to Ohm's law. So right away, I know that's 8 volts. So if that's 8 volts, then look what happens here. This tells me here that if I now look at this point here, I have a resistor here, and I have my 4 volt here. Note that this guy is 4 volts. Now we know that that guy is 8 volts. And so what ends up happening? You could see here is that if this node is this guy right here, and let's say that I make this node green right here, you could see that this node right here now becomes 12 volts. Okay, so I know that is 12 volts. Now the next thing I want to do is that I want to look at the voltage of the other node here. So when I look at that voltage of the other node, I'm going to call this resistor, let's call this resistor Y. And look at the direction of the current. That's positive, that's negative, so that's the polarity. So now if I look at the voltage Vy, that's also, excuse me, the voltage of the 2 ohm. But this tells me that I have what? That I have a voltage of 2 times 2 according to Ohm's law. So this guy is 4 volts. But look at how the nodes are set up. So if I look at this node, I have a resistor here, and this is my ground right here. So let's color this guy right here. So I'm going to call this guy orange. So note that on here, that means that this is orange right here. And then over here, that tells me that this guy is green. So if this guy goes in this direction like that, and this is 4 volts, you could see that that orange node must be minus 4 volts. So I could now see what is my high and what is my low. So in this case, I'm going to say that this is my positive node. Let's call that A. And then I'm going to call that B. So this is positive, this is negative, and now this is VC of 0. So the last thing I got to do here is that now the open voltage VC of 0 is then going to be VC of 0 minus is going to be VA minus VB. And so that should be 12 minus 4. That should give me positive 16 volts for VC of 0 minus. So now I know what my initial voltage is. So now let's go to the next thing here. So now I've determined that. So now, because this is a capacitor, I'm going to go to step 2. And in step 2, I'm going to determine the Thevenin parameters. At t equal to 0 plus. Now remember, what are the Thevenin parameters? VOC, RTH, and 1 over tau. So here we go. So the first thing I'm going to do, I'm going to determine VOC. So now I have removed the load, okay? So if I remove the load, we could then see here that the switch kills off the 4-volt source. Okay, right? That switch right here kills off that 4-volt source. So that means I really have this circuit right here. That's what I'm going to draw. So if that's the case here, then I'm going to, because of the open, I'm going to follow the current. So because of the open, follow the current of the 4 ohm source here. So here I go. So I'm going to draw this guy. And then here's my open, which I'm now going to call that B. I'm now going to call that A. And I'm going to use the same ground as before. And then I have my current source right here. So this is my circuit here. So once again, let's go see what do I see here. The first thing that I see is that, let's put in the values. And then this is a 4, this is a 2, this is a 2 right here. And so now what I'm going to see here is that, note that this whole thing right here is our ground. So this immediately tells me that if I choose this guy to be plus, minus, and this is VOC, I immediately see by inspection VA is automatically 0 volts. Now follow the current. Here comes the current. So here's my 4 amps. Here's my 4 amps. And look what happens. As before, I have 2 amps going this way. I have 2 amps going that way. And you could see that I'm going to get a polarity of plus and minus here. So if I, just by looking at this thing, what I'm going to see here is that, again, the voltage of that 2 ohm resistor is 4 volts. 2 times 2 gives me 4 volts. So then when I look at node B, you could see here is that I'm going to get this node again right here. And this node has to be minus 4 volts. So if I'm a little bit more detailed here, we could then see by inspection that VB then has to be minus 2 times 2, which will be minus 4 volts. So from these two right here, we then see that VOC should be VA minus VB. And I'm going to get 0 minus minus 4, which then gives me plus 4 volts. And here's my VOC. So we have an important check here. So now let's do the important check. Initially, we interpreted the caps voltage and found it discharges. In other words, VC of 0 minus has to be bigger than VOC. So now, is this true? Let's go check it. We see that VOC is 16 volts. So we then see here is that VC of 0 minus is 16 volts versus VOC, which is 4 volts. And note that this is correct. So, as expected, right? As expected, the cap discharges. If it did not do that, you would have had to gone back. Okay. Now let's go to the second piece. So now what I want to do here is that I want to determine RTH and 1 over tau. So I'm going to use method 1. So remember, I still have the circuit from over here. So what I got to do here is I have to open the 4 amp source. Okay, so I'm going to use method 1. That opens the 4 amp source. So if I look at this thing, here's my circuit then. So I'm going to have a 2 ohm, another 2 ohm, a 4 ohm, and then here's my open right here. Here's B, here's A, and so here's 4, 2, 2. So then I want my RTH right in between here. So if I look at that, there's lots of ways to look at this thing, but you could see if I follow the current comes here, and then one goes here, and then note that you could see that these guys, the 4 and the 2, are in series. So if I look at this thing, you could then see that RTH is then going to be 2 parallel to 4 plus 2, and that has to be what? 2 times 6 divided by 2 plus 6, which then gives me 3/2 kilo ohms for RTH. So now I want to determine 1 over tau. So 1 over tau is then going to be RTH times C divided into 1. So now I'm going to start putting in my values. So this guy's going to be, so you could see instead of 3/2, when I put in the denominator, it becomes 2/3 K. And then my capacitor is 100 microns. So when I compute that, I get 20 over 3 hertz, or 1 over tau. So now I have the parameters that I need. So now what am I going to do? I'm going to go to step 3. And I'm going to put this into solution form. So if I put this into solution form, what do I see here? I see that VC of t should be VOC, VC 0 minus VOC e to the minus t over tau. So then I'm going to get, so if I plug in all my values, I'm going to get 4 plus 16 minus 4 e to the minus 20t divided by 3, which then gives me 4 plus 12 e to the minus 20t3 volts for VC of t. So now, what do I know about this? What I know about that, that plus sign tells me what? That it discharges. And then that 12 tells us that it discharges by 12 volts. So if I look at this thing graphically, what does it look like? So if I now plot this thing, I'm now going to see this here. So graphically, I'm going to have a curve that looks like this. And what I'm seeing here is that this guy comes in at what? VC of 0 minus is equal to 16 volts. And this guy is going to completely discharge to VOC equal to 4 volts right there. So that means it's going to decay all the way like that. And so what you're seeing here is that if I measure the difference between here and here, you could see that there's a 12 volt drop. So picture-wise, that's what that equation is showing us. But now what we have to do here is that we need to go to step 4 and we need to solve the problem here. So now we're on step 4. We need to solve the circuit problem for Ix of t. So let's go do that. So what I'm going to do here is that I'm going to go back to our original circuit. So I'm going to go back to the t equal to 0 minus circuit. Now note, we've already written this out. So if I come all the way back here, I'm going to copy this circuit and bring it with us. Okay? So if I look at this guy, here is my circuit at this point. So the only thing I care about is I care about Ix. So what I'm going to do here is that I don't care about this guy right here. And what I do know is that we have defined this current right here as Ix of 0 minus. So by looking at the circuit here, here's what we have. You could see here is that Ix by inspection has to be negative 2 amps. So by just looking at this, so by inspection, we see that Ix of 0 minus is minus 2 milliamps. Now note, that's important that you do this because resistors in general have a discontinuity. So now, here I go. Now what I'm going to go do here is that I need to determine Ix of t at t equal to 0 plus here. So if I do that, what do I have here? Well, the circuit at t equal to 0 plus. Now note, we have that already, right? This is the circuit that we actually have right here, right? This is the circuit at 0 plus. So if I was to copy this, and then I'm going to modify it now. So if I come in and I paste the circuit, look what happens now. What I have here is that I don't have these nodes here. So again, I'm going to clear all of this stuff up because it's not true anymore. And the reason why it's not true is that I now have my capacitor right here. I think I should have just drawn this from scratch. It would have been easier. So then I have my capacitor right here. And the only thing that I know here is that this guy is Ix of t right there. But we know that the voltage of the capacitor, this is Vc of t here. So this is our circuit right here. So what you're finding here is that note that the 2 ohm is in parallel with the cap. Right? So if I look at this node right here, and I look at this node right here, you see that there are 2 common nodes, but they have opposite polarity. Because this guy has a polarity like that, and you can see that the cap has the opposite. So therefore, I could write that VC of T has to be minus the voltage of the 2 ohm resistor, but that's minus 2 times Ix of T. So now I can now solve for Ix of T. So if I solve for Ix of T, you can see that Ix of T is going to be minus 1/2 the voltage of the capacitor, but we know what the voltage of the capacitor is. That's it right there. So then I'm going to come in and I'm going to put in my 4 plus 12 e to the minus 20t3. And so that gives me a value of minus 2 minus 6 minus 20t3 milliamps, and that is Ix of T. So I now know what that is. So now, here we go. So what we want to do here is that we want to summarize we want to plot and interpret Ix of T. So if I look at in summary here, I get minus 2 milliamps, and then I get minus 2 minus 6 e to the minus 20t3, also in units of 1 milliamp. So this guy is going to be at t less than 0, and then at t 0 like that, you're going to see that this guy is now Ix of T. So I haven't done anything new. It's the same thing that we did. So what we want to do here is that we expect a discontinuity in resistors when a switch is thrown. So that means that really tells me that Ix of 0 minus should not equal to Ix of 0 plus unless the circuit tells you. So let's compare them. So the first thing that I should do is that we should calculate Ix at 0 plus first. Okay, so here I go. So I'm going to use my second relationship. So I'm going to get that this tells me here is that Ix of 0 plus is then going to be minus 2 minus 6 e to the 0, which then gives me minus 8 milliamps for Ix of 0 plus. So now if I compare them, you could see here is that Ix of 0 minus, well, that one is just 2 milliamps versus Ix of 0 plus, you could see that's minus 8 milliamps. You could see right here is that these guys are absolutely different. So in other words, we have a discontinuity right there. So that clearly shows that Ix of 0 minus is not the same as Ix of 0 plus. Okay, that's the first thing. And then the other thing that we should see here is that as t goes to infinity, we then see that Ix at infinity is then going to be equal to 2 minus 6 times e to the minus infinity, which of course, this goes to 0. So the steady state, the final steady state is 2 milliamps. Okay, so let's go look at that. So now what I'm going to do here is that I'm going to plot it. Plot Ix of t. Now, as I plot this thing, everything is going to be below the axis. So here I go. So this is Ix of t. And so I'm seeing this here. So this guy's coming in here. And this is Ix of 0 minus. I get minus 2 milliamps. And then what you see here is that at 0 plus, there's a discontinuity right here. And this continuity tells me that Ix of 0 plus, this is minus 8 milliamp. So it instantly drops. Now look at that steady state. The steady state says that it's at negative 2 milliamps. So if I follow this line out here, what I expect to happen is that now this guy is going to go from here and it's going to reach the steady state right there. And so what you're seeing here is that this is Ix of infinity can be approximated to Ix of 5 tau, which is equal to minus 2 milliamps. So when this almost reaches that final steady state, I'm going to say that this is 5 tau. So at what time is 5 tau here? So 5 tau is then going to be 5 times 3 divided, nope, I got it wrong. It should be 3, nope, I keep doing that. It's got to be 2 divided into, oh man. Look at that, the time constant is what? It's minus 20 over 3, so therefore this has to be 20 divided by 3, and this gives me 0.75 seconds. So that means that this is 0.75 seconds. That means it reaches steady state at roughly 0.75 seconds.